Students, I welcome you all in physics classes. Topic of today is electric field due to an electric dipole on equatorial line. First of all, let us know what do you mean by equatorial line. So remember, a point lying on the perpendicular bisector of an electric dipole is called point on equatorial line. To calculate electric field due to an electric dipole at a point on equatorial line, we consider two charges plus q, minus q, separated by distance 2l. On its perpendicular bisector, that is on the equatorial line, at distance r there is a point P where electric field intensity is to be calculated. You can see that electric field due to charge plus q at the point P is E1, which is in the direction A to P, and the electric field due to charge minus q is from P to B. From diagram we can see the distance of P from point A or point B, that is AP, is equal to BP, equal to square root r² plus l². So the value of electric field at the point P due to charge plus q is given by E1 is equal to kq upon distance square, that is AP square. Here the distance of point P from A is what? AP, and we have shown that AP is equal to root r² plus l². So the electric field E1 comes out to be kq upon r² plus l². This electric field points from A to P. Side by side, electric field at point P due to charge minus q. Now we are going to calculate electric field at point P due to charge minus q, that is equal to E2 is equal to kq upon r² plus l². The charge is same, magnitude of charge is same, distance is same, so the value of magnitude of the value of E2 and E1 will remain same. The difference is only that of direction. The direction of electric field is from P to B. The direction of electric field is from P to B. Students, electric field is a vector quantity. That's why we can resolve it in components. The electric field may be resolved in components. I am going to resolve E1 and E2 into the component E1 cos theta and E1 sin theta. Similarly, E2 is resolved as E2 cos theta and E2 sin theta. Since the magnitude of E1 and E2 is same, that's why these vertical components, being equal in magnitude, opposite in direction, will cancel out. The magnitude of vertical components, the magnitude of these vertical components here is equal and opposite in direction, so they will cancel out. While these horizontal components, that is E1 cos theta and E2 cos theta, are in the same direction. So we can say total electric field at point P is equal to E1 cos theta plus E2 cos theta, or you can say 2 E1 cos theta, because again I am reminding you, magnitude of E1 is equal to magnitude of E2. Substitute the value of E1. The value of E1 is kq upon r² plus l², and the cos theta from here you can see cos theta is equal to base upon what? Hypotenuse. That is L upon square root r square plus L square. Already we have studied twice of QL to QL equal to P, that is electric dipole moment. So formula for electric field due to dipole at point P comes out E equal to Kp upon r square plus L square whole square what? 3/2. The value of K here you can substitute 1 upon 4 pi epsilon naught. Therefore, electric field final expression for equatorial line comes out E equal to 1 upon 4 pi epsilon naught P upon r square plus L square power 3/2. If we talk about an ideal dipole, we know an ideal dipole, the length is negligible. So for an ideal dipole, R is very greater than L. In that case, neglect L square. If you will neglect L square, you will find the electric field is equal to 1 upon 4 pi epsilon naught P upon R cube. So this is the expression for electric field due to dipole at a point on equatorial line. Students, the question is that what will be the direction of this electric field? We know yesterday or in the previous lecture we have studied the direction of electric field at an axial point. At an axial point is in the direction of electric dipole moment, that is from negative to positive charge. But here you see the direction of resultant electric field I have shown by red arrow, and it is from positive to negative charge. So we can say electric field due to dipole at a point on equatorial line always points opposite to electric dipole moment, because electric dipole moment is from negative to positive charge, and here the electric field is from positive to negative charge. So it shows that electric field due to dipole at a point on equatorial line is anti-parallel to electric dipole moment.